used to speaking in front of such a large crowd with a microphone and the whole deal. Today I'd like to give you an account of the progress I've made so far in what is an ongoing project to better understand the Shroud image using image processing methodologies. Let's see if I can make this thing work. First you got to turn it on, I guess.
Yep.
That makes sense. Okay, a little motivation. I was actually inspired by Mario Landandresi's, I don't know, I probably butchered his name. He wrote a JavaScript app that puts up Shroud images and lets you make length measurements on it. And I got him an image, and I put his thing on his application on my website. And that was sort of, I think that more quantitative material, especially on the image of the Shroud, would be kind of helpful. And so he kind of inspired me. And of course, Barry Schwartz has been a friend of mine for every time I run into him. We renew our acquaintance and we have long telephone conversations now and again. Barry, I got a copy of his STIRP images some time ago. And when I joined the Shroud Science Group, it was Giulio Fonti was kind enough to send me some high-resolution scans of the Durante images. So with those materials at hand, I had no longer had any excuse not to actually do some work instead of just talking about it. So I whoops, I got going the wrong way. I approach the Shroud image from the standpoint that there are levels of analysis. You want to start at the raw data level, where there are quantitative observables, typically the RGB values in the images. There's a lot more than that. There's another level, a little higher level, called recognition, where you start to categorize the data into elements: cloth, image, blood, scorched dirt, various things of that nature. There's an aggregation level where you sort of integrate what you see into more features so that we understand: face, wrist, arms. And finally, there's the contextual level where we ascribe meaning to these things: wounds, scourging, crucifixion, that sort of thing. I'm going to restrict my comments to the first two levels at this stage of my work. The initial result, I started out by taking some of Barry's images and trying to figure out how to do some manipulation of the images on a point-by-point basis. And one of the things I thought I wanted to do was to try to understand better the banding. Banding has always been a big interest of mine, and one of the things I wanted to do was sort of normalize the image. So one of the first experiments I did was to normalize the image in red. What I basically did, I took all the RGB pixels and I multiplied each pixel by a multiplier that would drive red to 1 or to 100%. And the interesting thing that happened that I thought was quite interesting is, for all practical purposes, the bands disappeared. All the vertical banding pretty much disappeared. The horizontal banding was diminished. And you saw more of the cheeks and more of them, and Barry has talked about that. And I was so happy with that result that I thought, well, that's cool. I'm going to be able to do something. So I started thinking about what I wanted to do, and I'd like to have some long-range objectives. I don't believe in like isolated projects. I'm sort of one of those space program kind of people. So I wanted to develop, in my mind at least, a comprehensive image study program, and you'll hear a little bit more about that if you hang around for my other talk, I think on Sunday. I wanted to compare multiple images, do feature characterization, study banding, image, blood scorch, all those things. I wanted to approach color normalization so that you could sort of compare images across images, blood image enhancement, a lot of things of that nature. But one of the things I really wanted to do was develop some means of involving younger researchers, because I just noticed that all the people I ever saw involved in the Shroud of Turin were getting grayer. I went to I've been to a number of Shroud meetings, and I can remember Barry when he had more hair. In fact, I can remember some people that now don't have any hair when they had hair, and things of that nature, and I'm not getting any younger myself. So I thought, you know, I haven't seen too many young faces, so we need to do something about that. Now, to do this, in my case, I needed some tools, so I started looking around at the tools that were available to do things like feature analysis and pattern recognition and that sort of thing. And there are a lot of tools out there, and a lot of them are free. You know, free like no money. The gentleman in the back was asking how much funding we have. None. Whatever we invest is the funding we have. In my case, I invested about $2 grand in MATLAB because I really like MATLAB as a tool. Unfortunately, I also didn't buy a workstation because my wife made me buy furniture that was equal to the price of MATLAB. She's not here, so I can say that. She is here, but she skipped out. She says I'd be bad luck if she was at my talk. Okay. A couple of the things that are available, CVIP Tools is free. It's often used to teach image processing. ImageJ is a really cool tool in Java that is free by the subsidized by the National Institute of Health. You can get it. I'm part of a web email service that I get 40 emails a day from this crowd that are using ImageJ to analyze medical images. I can't keep up with the data of how they do it. So there's a lot of tools out there. Photoshop Elements is a nice inexpensive tool that lets you do a few things. If you're into programming, and I teach computer science, Python is a cool scripting language, and the Python imaging library, which isn't terribly extensive, is still good enough that you can do an awful lot of things, because it'll pull a pixel out, you can play with the pixels, you can do filters, do all kinds of cool things. So that's kind of where you can get started. Today I want to talk a little bit, give you an interim progress report on the work I'm doing. My primary focus today is in image segmentation using color and luminance and weave striations. I started with 2 steps. I wanted to determine some classification metrics for samples, and I wanted to make color substitutions in order to sort of visualize the results, and you'll see what I mean in a minute. Here is an example of 19 samples that I took from the Shroud. I love this thing with images because you can almost imagine yourself with a little pair of scissors cutting samples out of the Shroud. Here are my 19 samples. You know, I didn't have to cut the Shroud up. I got 19 samples. The interesting thing that I think you should notice is how similar these samples are. Their scorch is very dark, but that's almost the only difference. Anything that starts with a B is a blood sample. These lighter ones are cloth that doesn't have any image on it, and the ones that are sort of in between are cloth that has image on it. But you have to say, looking at the whole deal, there isn't a whole lot of difference, and that's an issue. Here's where the samples are taken from. Because my computer only has 2 gigabytes of memory, boy, I would have been interesting. My first computer was an Apple II Plus, and it came with 48K, and for an extra $500 or something, you could get another 16K of memory, so you had a whole full boat of 64K. Now I got 2 gigs, and I have a hard time loading the image. So I have a 541 meg image that Julio sent me. I load it and I can cut things out of it. I don't have enough memory to really do anything too impressive with the whole image. So what I did is I cut this guy out and I called him the face crop. Each of these little markings is, this is a B1 is a blood sample taken at the foot. Most of the image samples, like 4 of them, are taken in the face area because that's where I stressed a lot of my processing. Here's what CBIP tools looks like with the 8 blood samples in it. I just wanted to show you what one of the tools that you can get for free. You can just go to and pull this down offline and play around with images yourself. You click on these things and they've got a wonderful, I'm interested primarily in authoring my own routines, but this thing lets you do that as well. But you have to learn C. If you don't know C, then maybe you should look at image J. Then you can do it with macros. Image J has macros, and you can also author in Java. If you don't do any of those things, maybe you need Photoshop Elements or something, and you can play with that. But here's the problem. Everything is everywhere. When you look at the Shroud, you discover almost no matter how small the sample, you find little bits of different things. And now you can't really, this is a metaphor, the blood is obviously something that's added. Dirt's something that's added. Image, we don't know what image is. It appears to be desiccated linen. Ray Rogers thought it was a Maillard reaction in a very thin 200 nanometer layer of polysaccharides on the surface of the cellulose. Julio thinks it's due to coronal discharge. We argue about that. I don't know what it's due to. Sue was kind of thinking about calcium carbonate somehow mediating the process. A lot of cool things, but I do know that it'd be nice to figure out some characterization of it so you could say this pixel's image and this pixel isn't. That's a little difficult. Color spaces that I tried to use, you start with the RGB true color space. Now RGB means red, green, blue for those people who've never looked at how an image is represented. And each of those colors in, if it's a uint8 image, and that's a MATLAB term, it stands for an unsigned integer of 8 bits. Each of the color dimensions is represented by an 8-bit number. That means you can have 256 shades of red alone, and 256 shades of green, and 256 shades of blue, and when you combine those together, you multiply 256 cubed, and you get a big number. A whole bunch of different colors. There are, these are the color spaces I use. This is the one the images tend to come in. It's called RGB True Color. Then what I do is I convert them to unit vectors and a luminance value. That allows me to isolate color and brightness or luminance. That gives me 4 dimensions though, and I don't really want 4 dimensions. I want 3 dimensions. So I take the unit vectors and I turn them into a direction, which is a phi theta. That's a direction in color space, and then the luminance. Finally, a 4th color is, you use binary is really helpful because binary images let you make masks where you can go in and say, I want to pick this bunch of colors out because they have some property that I like. Okay, here's some samples. The black pixels are all the color samples in the face crop image. The face crop image, if you might remember, is this guy. So that's all the pixels in the black. This is the whole color space, all the colors you can represent. The Shroud doesn't cover very much of the color space, pretty narrow. Inside that, the blue guys are the pixels in a sample that I called C1. It's a fairly large clean cloth sample. So the blues, the clean cloth's over here, the blood's over here. In between is sort of the image, but they're all clobbered together. And here's what it looks like when you blow it up. So this is a whole bunch of pixels from the Shroud, just to give you an idea of the coverage of the color space. If I take these 4 samples and I plot them now in phi and theta are the dimensions that create a color. And then luminance is how brighter. It's a third dimension of how bright it is. You get a little bit more, more difference if you take luminance into account. But it's still pretty tough to divide. Even blood obviously is very dark. So down is dark, up is light, and phi and theta are the two dimensions of the color space. Now, getting a little bit ahead of my story. One of the things I wanted to do was to actually end up dividing the image up into segments using predominantly color and maybe combining luminance in order to classify each pixel on the shroud with whether it's blood, image, cloth, automatically under computer control. This is a kind of an experiment. One of the first things I did is I took a bunch of samples of isolated blood, and I said, okay, what's the color range for blood? Let's substitute bright red every place that a pixel matches that set of properties. And one of the things you discover is that you can do that pretty well. Blood's really nice because it's one of the darkest things on the shroud, and it pops right out. One of the interesting things is when you do that, you get little red flecks in a lot of other places too. Places where blood might reasonably be. If you were bleeding all over your face, you'd expect to find some blood sticking in your mustache, in your eyebrows, in your beard. So it makes a certain amount of sense. If you're carrying a cross and you fall on your face, you're going to damage your nose. They did a nice scene like that in the Passion of the Christ, I thought. So color injection is kind of a nice, let's go back to that, it's kind of a nice little way of highlighting something and taking a look and seeing what it produced. Here's an example, another example using a different approach. Here I used indexed images, and an indexed image is where you take the original image, you break it down into a number of colors. Now in this particular case, there was an intervening step where I took this image and I turned it into just unit vectors, which is just color. I took out the luminance. And then I substituted, after breaking it into 8 only colors, I took 3 of the colors that seemed to be correlated with blood and just plugged red in for those colors. And you can see it did a nice job, but there's some problems. This is a little scorch. At least I think it's a little scorch. But
Scorch or water stain?
it's something. It's something that is probably not blood, and it's kind of making the cut, which is not.
I believe that's a water stain.
Do you? Okay, I'm not positive. Here's an example of how the color segmentation works when you're moving from one colors from the original RGB true color space. You do the unit vector conversion and you get, this is the colors, can't see very much there, and this is the luminance. If you do a contrast stretch on the color unit vector, you get this, which shows that it's potentially possible to do an awful lot of separation with just the color. Here, notice that here the blood comes out kind of magenta, and this little thing here comes out sort of orange. That's kind of it. And here's doing that same process for the whole face crop image. You see the same results. Now the image comes out sort of orangish, the blood is magenta, the scorch mark over here comes out bright orange. So there's some suggestions that you can do some pretty interesting things here. I want to skip ahead. Here's the same process being the nose image. I picked the nose image to study because it's a place where you have a maximum amount of vertical relief. You got it close to the cloth here, and yet it kind of a gradient back to the forehead. So if you're going to find image anywhere, you probably will find it in there. Here's yet another thing. This is in interesting because it's a unit vector color segmentation. The unit vector color image was contrast stretched. Then I went in and I converted it to 16 color indexed image. And the thing I found interesting is then I plugged in only the false color black. And I substituted the false color black for the RGB pixels, but only for the colors that had either the largest pixel was red, or the largest pixel was green, or the largest pixel was blue, and that gave me these three images. When I substituted for red, the face pretty much darkened. When I substituted for green, you got the cloth turned blue. When I substituted for blue, the cloth turned green. And so I plugged in black for both the max green and max blue, and out comes the image here. Now, one of the interesting things about this image is I think I didn't invert this image. This image was just contrast stretched. I plugged, it started out as a unit vector color image that was contrast stretched, and then I plugged for green and blue, I plugged in black, and the image looks like a positive in red. But it started with the negative image. So the only thing I really flipped was the color, was the cloth. So that's an interesting characteristic of the image. Now, Kevin Moran mentioned it to me, and I said, well, you know, I kind of saw that myself. Now, here's another example of false color. You can plug false color, and here's what I'm doing. I started out with the Shroud image. I converted it to 24 index color, and I started plugging black in for the darkest pixels and white in for the lightest. And it's just interesting to watch the gradient as you plug in black. Any pixel that wasn't plugged with white or black is the original color. So slowly as you add, you're sort of stretching the image and creating a contrast image. So what it all comes down to then is, what am I going to do to try to get this color segmentation thing to work? Well, one of the things I thought of is, well, let's go into the unit vector color space, and we'll pick a color, and we'll pick a range in color space, an angular range around that color. And then we'll go out and we'll pick a range of luminance. And here's what happens if you pick a fixed color, and then you open it 3 degrees to either side, so you'll take any color within 3 degrees. So that's plus or minus 3 degrees, that's not 3 degrees. And then you take luminance 0.3 to 0.7, you pulled out the blood pretty well. If you move that luminance up, now bigger numbers mean you're taking lighter things. You'll lose some of the darkest blood and you pick up more pixels. You sort of see the way this thing, the false color spreads as you open that up. Here's another example of doing the same thing, where I'm trying to understand the difference between opening up luminance and opening up color differences. And here's false color across the nose, the cheeks, where I've just split the luminance up into 3 pieces. The lightest luminance is presumably cloth, or at least things that are the lightest. Intermediate is mostly image, and the dark things also tend to turn out to be blood. So I was kind of, at this point, not sure what the best way to proceed was. I started looking at something that I thought was really interesting, which is that if you take the individual samples, you can split them by doing a medium split contrast. You can split them into stripes and interstitials. The stripe is the dark part of the weave, and the interstitial is what's in between. And then if you do this conversion, you can then go back in and pull the colors out selectively. So I went in and pulled the colors out selectively for these 3 categories: cloth, image, and blood. I looked at the scorch, but I didn't use it. And then I classified each of these in rho theta and phi theta luminance space. And I created a separate classification for blood and for interstitials, and for interstitial blood. And then here's an example of taking the original, say, wrist wound. If you stick in the interstitials, you'll see that the interstitial pretty much catches all the interstitials, but as you move outside of the wrist wound area, you start missing that threshold, because it's a threshold between the blood. If you do the same thing with the blood interstitials, you pick up the blood and you combine the two. Well, that's interesting. Well, can we transfer this? Well, I took the same thresholds which have been normed on the wrist and transmitted them to the chest wound, and it worked pretty well. So this is, I take the wrist, move it to the chest, and it works just as well on the chest, even though I didn't use the chest blood data for that. So that shows that you can transfer data from one part of the shroud to the other. This is some data. I won't go into this because I'm running out of time. This is color and luminance. This is some data about when you take the values. Notice these. This is the color in phi theta space. This is the color of the stripe. This is the color of the interstitials. They are almost exactly the same, which means that despite the fact that they're different in brightness, they're almost exactly the same color. When you do the median split, for different blood stains, the median is at different places. So there's more or less blood in these different places. If you try to then come up with a general classification scheme, one way to do it is take means of each of these properties in the color space, and then take luminance into account in addition, and you can create a set of rules. And what I did is I created a set of rules. This is my first cut, basically, on doing it. This is a completely false color image of the shroud face, where what I've done is I've taken wherever the algorithm here is to go in and classify the pixel based on what it's closest to. If it's closest to cloth interstitial, make it white. If it's closest to blood interstitial, make it bright red. If it's so I've got 6 categories, and I tried to pick the color so I get something kind of shroud-like, so I wouldn't totally distort the image when it came out. And I think it worked out pretty well, not as well as I would quite like, because I have an awful lot of gray, which is really blood interstitial, intermixed in image areas. So what happens is the blood interstitial overlaps. The color of the interstitial blood overlaps with the stripe image, and you can't discriminate the two, even though I've taken into account both color and luminance. So what I'd like to do, I've got a lot of ideas to continue. The shroud, a few interim conclusions. The shroud is characterized, as should not be a real big surprise, by a very narrow color luminance space, which makes classification by color alone difficult. That's probably an understatement. Contrast stretching might help. You saw how much of a separation you get when you contrast stretch the unit vector color images. You can do a regional analysis of stripe and interstitials, and that separately seemed to improve segmentation. So I'm kind of hopeful that a combination of techniques could be employed to make the segmentation better. The image area shows a strong affinity with the interstitial blood modes, as well as having pixels that are likely evidence of blood or on the nose, mustache, and beard. That's not a really new result, but I think some of the ways that I show it, I think I narrow it quite a bit. Some further work. I'd like to extend the work by exploring more selective substitution schemes. I'd like to add localized region statistics to the classifier. That would, I think, make it more robust. I'd like to explore fine-tuning using color and luminance gradients. So I introduced the gradients of the color. This is a point classification. I gotta get really, really good pretty well considering the limited amount of data. But you can do a lot better with more regional statistics. That's where you study the texture of the region, not just its color. This is strictly based on color and luminance. Explore the relationships further by extending the categories. I'd like to extend the categories to scorched water stain margins and detritus. I'm not sure I pronounced that word right. Dirt droppings, little droplets of things that are on the shroud, maybe flower bits. I'm not sure what they are. I'd like to acknowledge a few people. Mario Latendrisi, whose initial work inspired me. Barry Schwartz for his images and his friendship. Giulio Fonti for, frankly, without this I mostly use Durante 2000 for this work. And all the Shroud people who've been inspiring to me over the years, especially Dan Scaloni, whose historical work has always been an inspiration to me. Thank you very much.